Assalamualaikum warahmatullahi wabarakatuh. So today our group will be presenting a proving technique which is quantifier. So what is quantifier? Quantifier is an operator that specifies how many individuals in the domain of discourse satisfy an open sentence. Next, open sentence is a declarative sentence that contains at least one variable. Next, quantification. Quantification is an open sentence that can be converted into a statement. By adding some specific phrases, it will become a quantified statement. Next, there are two types of quantifier. First is universal quantifier and the second is existential quantifier. Under these two types of quantifier, we also will be learning one quantifier, one variables, two variables, and basic connective.
The definition is the universal quantification of Px is the statement Px for all value of x in the domain. The notation is for all x Px or for every x Px. The symbol of all is called universal quantification. For example, let Px be the statement x less than 4. What is the truth value of the quantification for all x Px where the domain consists for all positive integers? For the solution, finding just one counterexample is enough to make for all x Px are false. For example, P5 is less than 4, so it will be false. As P5 is false, therefore x equal to 5 is one such counterexample for the statement for all x Px. This shows that Px is not true for every x in the domain of positive integers. The quantification of Px is the proposition there is an element x in the domain such that Px. This means that there must be at least one element in the domain such that Px become true, or we can say that there is x Px. Now, here is one important point for you to note. Specifying the domain is important. Without domain, the statement there is x Px has no meaning. It should be well known that if you did not specify the domain, then this statement has no meaning. There are different ways to say that there is x Px. You can say here, you can say there is an x such that Px, or there is at least one x such that Px, or for some x Px. Here is one example I would like to discuss for cementing the concept of existential quantifier. What is the truth table of there is x Px where Px is the statement x squared 2 greater than 10? And the universe of discourse consists of the positive integers not exceeding 4. We know that Px is the statement x squared greater than 10. Now, if we can replace this x by 1, then we can say that 1 squared greater than 10. Please note here, the domain consists of positive integers not exceeding 4. So the domain is 1, 2, 3, 4, right? You can see over here that with x equal to 1, we are getting the truth value as false. Now, what happened in case of P2? This will be 2 squared greater than 10. This is also false because 2 squared is 4. 4 is not greater than 10. Next, P3 also false because 3 squared is not greater than 10. In case of P4, this will be 4 squared greater than 10, which is true. So this statement will be true.
Quantifier one variable. It is easy to solve quantifier with one variable. As we can see here, the truth tables. So there are statements. For universal statements, we can see if it's true when every single element in Px is true for every x. Meanwhile, when is it false is when at least one element x in Px is false. Next statement for existential quantifier. So when it was true is when at least one element is true in Px. When it is false, it's false for all x. Okay, so for example, for every natural number x, 2x plus 1 is greater than 0. So at the top is the symbolic form for the statement. Next, how do we solve it? We just take the equation given here and replace the x with any natural number such as 0. Then we solve it, and if the answer is greater than 0, then so it is true. Then we need to put example x equal to 0. Next is a example for existential quantifier. So the statement is there exists a natural number x such that x power of 2 plus x plus 41 is a prime number, and the top on top of it is the symbolic form. So how to solve it? We need to let x equal to 2 and replace the x in the equation given with 2. So it will be 2 power of 2 plus 2 plus 41 equal to 47. Then we need to make sure if the 47 is the prime number. So as we can see here, 47 is a prime number, so it is true. And we need to put the example x equal to 2.
Alright, for quantifier 2 variable. Okay, so here's the truth table. For all x, for all y, p, x, y, the statement will be true if each pair is true, and if there is one pair that is false, then the statement will be false. Okay, for second, for all x there exists y, p, x, y. For each x there exists an y to make the statement true, and for each y there exists an x to make the statement false. Okay, third, there exists x for all y, p, x, y. For each y, there is an x to make the statement true, and for each x, there is an y to make the statement false. Okay, and lastly, there exists x, there exists y, p, x, y. Okay, the statement will be true if there exists a pair that is true, and the statement will be false if all pair is false. Okay, so here's an example to negation of quantifier. Express the negation of the statement. For all x there exists y, x, y equal to 1, so that no negation precede a quantifier. Okay, first we need to do, move the negation inside quantifier by applying De Morgan's law for negating single quantifier. For all will be converted into there exists, and there exists will be converted into for all. And for this question, first we need to negate for all, and it will be converted into there exists. And secondly, we need to negate there exists, and it will be converted into for all. And lastly, we need to negate xy equal to 1, and it will be converted into xy not equal to 1. Okay, this is an example for nested quantifier. Let x and y be the real numbers and pxy denoted xy equal to 0. Find the true value of the following. Okay, the first one is there exists y for all x, q, x, y. This means there exists real number y such that for every real number x, xy equal to 0. Okay, so here we need to prove that there is real number y to make the statement xy equal to 0. So let's say we put y equal to 0. Every real number x times y equal to 0, because every number times 0 will be equal to 0. So it is true. Again, and because it is true, we need to put out an example, which is if x equal to negative 2 and y equal to 0.
The last topic that will be covered in this chapter quantifier is basic connective. So let's take a look on example 1.
The question requires us to write a logical expression for the statement anyone that has ever received a perfect score on final exam is a genius. So firstly, we can define our own notation. Let g of x means x is a genius, and let p of xy mean x had a perfect score on final exam y, where x is a person. Then, by using these two things, we can construct a new statement in the symbolic form. But before that, we must know the keywords in the statement. So as we can see in this statement, there are three keywords that has been highlighted. One of these is anyone, which we need to use for all in our logical expression. Second, the term has ever that has to do with there exists. So that's a clue to use the existence symbol there exists. And the last one is. This will be our implies or conditional connective. And the expression will be for all x, if there exists a y such that p of xy, then g of x. So this is how we could represent this statement as a logical expression using the notation g of x and p of xy. Next, on example 2, we need to determine whether the statement is true or false. Given that for all x and for all y are elements of integer, such that x less than y implies x squared less than y squared. Since all of x and y are the elements of integer, where integer number can be any negative and positive number, so we may take negative values to test because it will be easier for us to figure out whether the statement is actually true or false. First, we may substitute x with -2 and y with -1. So for the first statement, it will become true because -2 is less than -1. Meanwhile, for the second statement, it will become false as we square both sides at -2 and -1. And the answer is 4 less than 1, which is false. Therefore, the statement is false since it is a conditional statement where when hypothesis is true and conclusion is false, then the statement will be false. The counterexample is when x equal to -2 and y equal to -1.
So, in conclusion, logic and proving are important in improving the quality of life. For example, in management, law, finance, history, and other disciplines, there are proof that can be introduced new techniques to solve other problems in mathematics or offer understanding for something different from the original context. We will be able to broaden the range of things we know and understand. Therefore, logic and reasoning are important to remember and be applied for the best or most desired results.